all the examples we have considered, one thing stands out, and that is that all the x omega we have at hand are periodic with a period 2 pi. X omega equals x omega plus 2 pi. This can be verified for all the 3 examples that we have presented. Thus, this is one of the most fundamental properties of the DTFT, the periodicity with period 2 pi. This is one of the most fundamental properties. Now, given this periodicity, we will have to ensure that any signal in the frequency domain that we wish to find an inverse transform for, inverse DTFT for, must first of all be periodic with period 2 pi. Otherwise, it is not even a valid continuous function of capital omega. That is to say, it is not a function which is amenable to the inverse DTFT. Next, keeping this in mind, let us move on and see if this DTFT, which is known to exist only for absolutely summable signals, that is to say signals such as signals which meet this criterion when summed over all n. This is the kind of signals we have considered so far in the 3 examples. What happens if these signals are not absolutely summable, but are periodic? Periodic and hence not absolutely summable. What happens then? This is reminiscent of the similar situation that we faced in the context of the continuous time Fourier transform, which was originally meant for finite energy signals, but which got extended to the case of finite power signals as well to give a unified formulation at a later stage. Let us see if we can repeat that performance over here, and the way we do that is to guess that Dirac impulses must have something to do with it. Suppose we place a Dirac impulse, or rather as is really required in the case of the DTFT, a train of Dirac impulses placed 2 pi apart from each other on the omega axis, and see what its inverse transform will be. So, we have, let us say, x omega equal to summation over all k delta omega plus 2 pi k. It is only a signal that is periodic with period 2 pi that qualifies to be the DTFT of some discrete sequence. So, now this does meet the criterion. Let us now try to find the inverse DTFT of this sequence, which is 1 by 2 pi minus pi to pi summation over all k delta omega minus 2 pi k e to the j omega n d omega. Clearly, out of the summation, only one impulse, namely delta omega, lies within the scope of the integral, within the range of integration. So, this becomes equal to 1 by 2 pi integral minus pi to pi delta omega e to the j omega n d omega. We now apply the shifting property of the Dirac impulse on this and find that the entire integral will evaluate to the value of the companion function at the point of occurrence of the impulse, namely omega equal to 0. So, that we get that this equals 1 by 2 pi. This means that 2 pi delta 2 pi times summation over all k delta omega minus 2 pi k is a function whose inverse DTFT equals 1. That is, x n equals 1 for minus infinity less than n less than infinity, which is clearly not absolutely summable, because it will blow up to infinity when you try to sum it. Here then is a clear case of a non-absolutely summable signal, which has shown to have a DTFT, which has appeared to have a DTFT. Now, let us take a more general example by not taking an impulse or a train of impulses located at 2 pi k, but at some arbitrary position omega equal to omega naught minus 2 pi k. So, we will take let us say x omega equal to summation over all k delta omega minus omega naught minus 2 pi k. What do we get when we find the inverse DTFT of this function? So, we get integral minus pi to pi 1 by 2 pi of the summation over all k of delta omega minus omega naught minus 2 pi k e to the j omega n d omega. This, if evaluated just as in the previous example, will give you that its inverse transform is e to the j omega naught n, which is a periodic complex exponential, which is clearly not absolutely summable. In short, we can say this it is actually equal to this divided by 2 pi, because there is this factor of 2 pi outside. So, we can say that e to the j omega naught n transforms to 2 pi summation over all k delta omega minus omega naught minus 2 pi k. So, this is another Fourier transform pair for a periodic signal, a periodic complex exponential. Now, we are equipped to take the next big jump and find the Fourier transform for any arbitrary periodic discrete time signal. If it is a periodic with period n discrete time signal, then it has a DTFS representation or a DFT representation, whatever we like to call it, of the form given by the synthesis equation. Thus, let x n be equal to x n minus n, so that we have x n equals 1 by n summation k equals 0 to n minus 1 x k e to the j omega naught k n. This is what we have. Now, what do we get? This is a sum of exponentials weighted by the respective x k's. Now, what do we get when we try? Can we try to find the DTFT of this sequence? This can definitely be done, because all we have to do is to treat each term in this expression in the same manner that we have handled a complex periodic exponential in the previous example. So, we will finally get x omega equals 2 pi by n, which is a common factor that lies outside, summation k equals 0 to n minus 1 x k summation L equal to minus infinity to infinity delta omega minus, remember that this kth component will occur at frequency omega naught, where omega naught is the fundamental frequency, minus 2 pi L, which takes care of the repetition with period 2L, with period 2 pi. This is the expression for the discrete time Fourier transform, or the extended discrete time Fourier transform for an arbitrary periodic sequence which has a set of DTFS coefficients x k, k going from 0 to n minus 1. So, this has now created a unified framework. This is a unified framework for the DTFT of both non-periodic and periodic, that is to say finite energy and finite power discrete sequences, discrete time sequences. Next item on our agenda is to explore the mathematical properties of the DTFT. Fundamentally, the DTFT takes infinite discrete time sequences into periodic continuous frequency functions. It is a 1-1 map between discrete time sequences and periodic continuous time or continuous frequency functions. Let us look at the various varieties that we have considered so far. Let us make a little table. We had the CTFT, then we had we first had the CTFS, continuous time Fourier series, then we had the continuous time Fourier transform, followed by the discrete time Fourier series, and now the discrete time Fourier transform. Each of them is related to the others in some way, and they all tie up together very nicely. The CTFT, the CTFS mapped continuous time periodic functions to discrete sequences, which were the sequences of the continuous time Fourier series coefficients, non-periodic discrete sequences. So, CTFS mapped periodic continuous time functions to non-periodic discrete sequences, discrete frequency sequences. Discrete frequency sequences. Next, the CTFT mapped non-periodic continuous time functions to non-periodic continuous frequency functions. Next, the discrete time Fourier series, also called the DFT, mapped periodic discrete time sequences to periodic discrete frequency sequences. So, all possible combinations, all possible pairs of continuous, discrete, periodic, non-periodic are manifesting themselves in this story. Finally, you have the DTFT, which maps non-periodic discrete time sequences to periodic continuous time functions. So, you see all possible combinations have occurred in one example or the other. So, with this summary of the relationships between the various transforms and series representations that we have considered, let us go and look at the specific properties of the DTFT. The first property that we consider is linearity. Which says that A x1n plus B x2n will transform to A x1 omega plus B x2 omega. That combines both superposition and homogeneity, that is to say additivity and homogeneity, and that is the end of that. Hardly any effort required to prove that. Next, conjugation. I am going to skip the proofs now, because whatever I do not prove is not proved only because it is extremely straightforward and can be drawn analogically. The proof can be evolved analogically with the corresponding proofs for the continuous time case. Conjugation x star n transforms to x star of minus omega. Time reversal is x of minus n, which yields x of minus omega. Since x of minus n goes to x of minus omega, we have automatically taken care of frequency reversal as well, because it simply means that x of minus omega goes to x of minus n, x of minus n goes to x of minus omega. So, this covers frequency reversal. Next, of course, is time and frequency shift. Time and frequency shift, and here we have, let us say, x n minus n naught, which will transform to a summation over all n of x n minus n naught e to the minus j omega n, which can be evaluated by just replacing n minus n naught with n dash and making all the appropriate modifications and manipulations that normally go with it, to yield e to the minus j omega n naught x omega, that is the multiplication by a linear phase factor e to the minus j omega n naught. Frequency shift would be where we had x omega minus omega naught. What would x omega minus omega naught do to us? It turns out that this transforms to e to the j omega naught n x n. All these are very, very easy to prove. So, there is no need to spend time on this in the middle of the course. Next, differencing and summation. Five. Differencing and summation. We know what is differencing. The first difference of x n of x n is defined as x n minus x n minus 1. Combining this with the time shift property we already have, this simply will have a Fourier transform given by x omega minus e to the minus j omega x omega. So, that this is equal to x omega times 1 minus e to the minus j omega. That is it. That gives you the first difference. Now, the opposite of the first difference or the inverse operation of the first difference is the running sum. Is the inverse of the running sum where the running sum is defined as y n is the running sum of x n if this is equal to summation from minus infinity to n of x k. This is called the running sum. As with the case of the continuous time running integral, this turns out to be nothing but x n convolved with u n, the unit discrete step. So, in order to evaluate the Fourier transform of the running sum y omega, we first have to evaluate what is the Fourier transform of the unit step. Once we have the Fourier transform of the unit step, we just need to multiply it, as will turn out later on when we do the convolution theorem. It will turn out that it is just multiplying the Fourier transform of u n with the Fourier transform of x n. But let us first find out the unit step and its Fourier transform. Fourier transform or DTFT of the unit step, discrete unit step u n. As we did, very similar to what we did in the case of the continuous time Fourier transform, u n is going to be expressed as a sum of a zero average part u 1 n minus or rather plus half, which is equal to u n minus half plus half. That is what un, this is the 0 average part and this is the average value. Now, what is the transfer function of the 0 average part? The 0 average part is u1 n equals un un minus 1. This is what we have, un minus half. Now, in order to find this, let us first find the Fourier transform of the first difference of u1 of n. The first difference of u1 of n is u1 of n minus u1 of n minus 1, which is nothing but equal to delta n. Now, what is the Fourier transform of delta n? We seem to be going astray, but we really are not. We are going from one problem to another, but we really are not. What is the Fourier transform of delta n? DTFT of delta n equals summation delta n e to the minus j omega n as n varies from minus infinity to infinity. Now, since delta n equals 0 everywhere else, this will have only one term which survives, and that therefore makes this become equal to 1, nothing more than 1. So, DTFT of delta n is known, it is equal to 1. Now, if its DTFT is known, then we can say, since delta n is the first difference of u1 n, delta n must be equal to the transform of delta n 1 must be equal to u1 of n u1 of omega multiplied by 1 minus e to the minus omega, e to the minus j omega. Fine. So, u1 n gets multiplied by this, because it is by multiplying by this in the frequency domain that we carry out the equivalent of differentiating, or rather differencing u1 of n in the time domain. So, you have this. Therefore, u1 of omega equals 1 by 1 minus e to the minus j omega. You have this. Finally, then u of omega equals u1 of omega plus the DTFT of half. Since the DTFT of 1 was the DTFT of 1 has not yet been found. So, let us just find it. We had that 2 pi summation over all k delta omega minus 2 pi k. This had an inverse transform of 1. So, we now have that half is transformed to pi summation over all k delta omega minus 2 pi k. This is half, is the transform of half. So, finally, u omega equals u1 omega, which turned out to be equal to 1 by 1 minus e to the minus j omega. It is this plus the other part, the constant part half, which is equal to pi summation over all k of delta 2 pi minus delta of omega minus 2 pi k. This is the Fourier transform of the complete unit step. With this in hand, which I will call u omega, since we know u omega now and we have x omega as the Fourier transform of x t of x n, then we can find what is the Fourier transform of minus infinity to n of x n dash, which is the running sum in terms of x omega. Now, this equals, as we said, x n convolved with u n. Okay. Now, we have the Fourier transform of u n, discrete time Fourier transform of u n, we have the discrete time Fourier transform of x n, but we still do not know what the convolution does. What is the Fourier transform of the convolution of two sequences? This we can very easily state. This is another digression. The convolution of two sequences x n h n transforms to x omega h omega. This can be easily shown by evaluating summation over all k of x n, summation over all n of x n convolved with h n e to the minus j omega n, which is equal to summation over all n of the convolution itself now is summation over all n dash x n dash h n minus n dash e to the minus j omega n. I am not going to carry out the remaining two steps that will lead us to this result, but it is not very hard. You just have to use the property of time shift and then repeat the exercise of finding the Fourier transform. So, you will get this particular result. With this result in hand, we are now in a position to evaluate the running integral, because it is the convolution of x n with u n, and hence finally the running integral from minus infinity to n of x n dash equals, as we said, x n convolved with h n u n is equal to, or rather transforms to, x omega times u omega, which is equal to x omega by 1 minus e to the minus j omega plus we can see the expression. If we go back for the second term, it is pi summation over all k delta omega minus 2 pi k pi x omega summation over all k of delta omega minus 2 pi k. This is what it comes to. But if we note that this x omega that this expression, this summation will be 0 at all points in minus pi to pi except for omega equal to 0. This can be simplified to x omega by 1 minus e to the minus j omega plus pi x times 0 x of 0 summation over all k delta omega minus 2 pi k. So, this has yielded the Fourier transform of the running integral of a function. So, having dealt with the differencing and summation effects, or the effects of differencing and summation on the DTFT, we will now see something else. What happens to x n if x omega is differentiated in omega? That is to say, if x n maps to x omega under the DTFT, then what maps to d x omega by d omega? That is the question we ask, and the answer is easily found by looking at the synthesis equation, the analysis equation. The analysis equation is x omega equals summation over all n x n e to the minus j omega n. Now, if we differentiate both sides with respect to omega, we find that the only quantity that awaits differentiation on the right side is inside the summation, it is e to the minus j omega n. So, this gives us d by d omega of x omega equals summation over all n x n minus j n e to the minus j omega n. Now, while the left side is this, is the frequency domain derivative of x omega, the right side still looks exactly like the analysis expression for a new function, namely this, for this function. Thus, this would be the inverse transform or the time domain sequence for which d by d omega of x omega is the DTFT. Thus, we get the pair that minus j n x n transforms to d by d omega of x omega. Fine. With that having been crossed, we will discuss something that is a little overdue by now, but which is relatively obvious to all of us, since we have already gone through it in considerable detail in the case of the continuous time Fourier transform, and that is the symmetry properties. The symmetry properties of the DTFT. Well, as I said, I will not spend time on deriving these properties or proving these properties. I will just list them out to you, and the way you prove them is exactly the same as you would do in the case of the continuous time Fourier transform, barring the minor differences that would come in. So, the first is that if x n is real, then x omega is conjugate symmetric. If x n is imaginary, then x omega is conjugate anti-symmetric. Conversely, if x n is conjugate symmetric, then x omega is real, and finally, if x n is conjugate anti-symmetric, then x omega is imaginary. As before, it yields interesting and pleasant results, like if x n is both real and even, then x omega will also be even and real, and several other similar results that one can derive at one's leisure. So much for the symmetry properties. Now, we introduce a notion which is unavoidable at this stage and which could have probably been introduced earlier, a notion of convolution of a different kind. We know how convolution is defined, but let us see what happens if you try to convolve two periodic non-zero signals. So, let x t, I am presently going to deal with continuous time signals, and then I will move on to discrete time signals. In both cases, the same point is being made. Let x t be equal to x t minus t, h t be equal to h t minus t, be two periodic signals. Now, the conventional definition of what is called linear convolution that we denote by this is x t convolved with h t as given by integral minus infinity to infinity x tau h t minus tau d tau. As far as non-periodic signals is concerned, there is no problem, but when x h are periodic, an integral, the linear convolution integral, will evaluate an infinite area. In short, it will not converge. Hence, carrying out a linear convolution of two periodic signals is out of the question. We cannot convolve two periodic signals. What we therefore introduce is something called periodic convolution. This is applied between two signals, both of which must be periodic. With the same period. Let us say with the same period t, as we have above with x t and h t just defined. Then what is the definition of periodic convolution? Periodic convolution, which we will define as x t periodically convolved, written by the convolution symbol enclosed in a circle with h t, is given by an integral not over an infinite interval, because that is what will make the convolution shoot off to infinity, but over one period. It does not matter over which period it is, but over one period. Let us say, for example, minus t by 2 to t by 2 of x tau h p minus tau d tau. Now, this quantity is certain to remain finite for all values of t, because the area, the interval of integration is only one period. So, while tau varies from minus t by 2 to t by 2, essentially you can say that one of the functions remains static and the other function is time reversed and shifted by the amount tau, as tau varies from minus t by 2 to t by 2, and inner products are evaluated at each value of tau, and these inner products essentially give you the value of h t. So, that is the periodic convolution. Now, why is it of interest to us all of a sudden? Before I even answer that question, let us just dispose of the periodic convolution of discrete functions, discrete time sequences. We have just now provided the formulation for continuous time sequences. For discrete time sequences, suppose you have x n equals x n minus n, h n equals h n minus n, then x n periodically convolved with h n is given by a similar definition. You have to sum over one interval. It does not really matter whether it is minus n by t to n by 2 or 0 to n minus 1 or whatever. We will do it from 0 to n minus 1. N dash equals 0 to n minus 1 of x n dash h n minus n dash. This is the circular convolution in continuous time, in discrete time. Now, where this becomes interesting to us is when we consider the next important property of the DTFT called the modulation property. Now, the modulation property is all about multiplying two discrete time sequences and seeing what happens to the DTFT of the product. So, if x x n transforms to x omega, y n transforms to y omega, we know that both y omega and x omega are periodic, that is to say that this equals x omega minus 2 pi, this is equal to y omega minus 2 pi. Taking a cue from the modulation property of the continuous time Fourier transform, what we expect here is that the Fourier transform of the product x n y n must be the convolution of the Fourier transforms, 1 by 2 pi times the convolution of the Fourier transforms. But unfortunately, here you really cannot carry out the usual or linear convolution of the two Fourier transforms, because both x omega and y omega are periodic functions with a period of 2 pi. So, how on earth can one carry out their convolution? So, the answer is obviously we carry out a periodic convolution of x omega and y omega, and therefore, it can be shown that x n times y n has a Fourier transform given by as a DTFT given by 1 by 2 pi x omega periodically convolved with y omega, where of course we fall back upon the continuous variable version of the transform as given over here. This is what we are going to use here, and this therefore amounts to 1 by 2 pi integral. Remember, the period is 2 pi, so you can say 0 to 2 pi or minus pi to pi. Let us say minus pi to pi for no particular reason, x omega dash y omega minus omega dash d omega dash. This is the Fourier transform of the product of the two discrete sequences x n y n having Fourier transforms x omega y omega respectively. So, that ends the set of most of the important properties of the DTFT.